Hi, welcome to the next video. We are now going to start 5.2. So 5.2 is on the natural logarithm. Okay, so we're going to discuss the natural logarithm in this class. So definition. The natural logarithmic function is defined by ln of x is equal to the integral from 1 to x of 1 over t dt, where x is positive. Okay, so the natural logarithmic function is defined by that equation. Okay, and so to illustrate what this definition is saying, let's draw this picture. So you have the graph y equals 1 over t. Okay, that's the curve y equals 1 over t. This is x, this is t equals 1. Actually, this is the t-axis. And then from 1 to x, let's say that's x. The area of that shaded region, the area is ln of x. Okay, so ln of x is the area under the curve y equals 1 over t from t equals 1 to t equals x, where x is positive. Okay. Now, also, if you have this area here, this is the t, this is the y-axis, this is the same graph, y equals 1 over t, and here's t equals 1. Now, instead of x being greater than 1, x could be less than 1. And if that's the case, if that's the case, then when you take the area between t equals x and t equals 1, now x is to the left of 1. And so that means that this area is negative ln of x. Okay. So that area is negative ln of x. This area is ln of x. It's the same definition. This equation is for both these pictures. But here you're integrating from 1 to x. And so here the area is positive, and so you're integrating to the right, right? You're integrating from 1 to x, and you get positive area. And so that's why the area is ln of x. Here, when you integrate from 1 to x, you're actually going to the left. And so when you're going to the left, when you take this integral, you're going to get a negative number. But technically, the area here is positive, and so that's why the area is actually the negative of ln of x. Okay? As the signs have to be adjusted because when you find ln of x, you're integrating from 1 to x. But if you look at this as an area, you're seeing this as a positive area because it's above the x-axis. And when you think of that, you would then be going to the right. But because we're going to the left, you have to take the negative of it to adjust the direction to the right. Okay? So that's confusing. So that's the definition of the logarithmic function. Okay, so this integral always exists because the integral of a continuous function always exists. 1 over t is continuous for t positive. So this is a continuous integrand function, and we're integrating it over this interval from 1 to x. And so you can always integrate over a continuous function. The integral always exists. Okay. And so just a note about area, right? So area is signed, like I mentioned. So for instance, this area is positive, right? This is positive area here. And if you have below the x-axis, then that's considered negative area, right? That's negative area there. So what's above the x-axis is positive area, what's below the x-axis is negative area. But, right, and so we're finding the area by integrating over an integral, right? But when we think of this as a positive area, we're integrating from the left x value to the right x value. And when we find this to be a negative, we're still integrating from left to right, from the negative x to the positive x. If we switch the direction of integration, if we switch the limits of integration so that the lower limit was not less than the upper limit, we switched it so the lower limit was greater than the upper limit, meaning we integrate in the opposite direction, the signs are also the opposite. So for instance, here we're integrating from left to right. If you integrate from right to left, when you have a curve, when you have area above the x-axis, we integrate from right to left. Now area above the x-axis is negative area, signed area. And if you integrate from right to left, if you integrate from right to left here and you have a curve below the x-axis and you find the area is now positive. Okay? So area above the x-axis is positive, area below the x-axis is negative if you're integrating from left to right. If you integrate from right to left, it switches. And so area above the x-axis is the negative and area below the x-axis is the positive. And so that again is the reason why this is negative ln of x. Okay, so that whole discussion is to explain why there's a negative sign there when the x is to the left of 1. Okay? So that is the definition of the natural logarithmic function. Okay, so let's do an example. Okay, so example A. By comparing areas, show that that 1/2 is less than ln of 2, less than 3/4. Okay, so by comparing areas, show that these two inequalities hold. Okay, so for that, let's look at the graph. Let's look at the area that corresponds with ln of 2. Right, so by definition, ln of 2 is the integral from 1 to 2 of 1 over t dt. I just substitute 2 for x. Right? The definition of ln of x is that ln of x is the integral from 1 to x of 1 over t dt. That's the definition of ln of x. So ln of 2, which is there, ln of 2 is just putting a 2 there. Okay. So we have ln of 2. ln of 2 is the integral from 1 to 2 of 1 over t dt. So let's draw a picture of that. We have y equals 1 over t, and we have from t equals 1 to t equals 2. And so this region, the area of that shaded region is the value of that definite integral, which is ln of 2. So that area of that shaded region is ln of 2. Okay? So now let's look at that shaded region, and now let's look at this point here. The height of y equals 1 over t when t is 2. So this point is 2 comma 1 over 2. So the height there is 1/2. So now let's draw a rectangle. So let's draw a rectangle where the height of the rectangle is the height of this point on the curve here at t equals 2, and the base is that. Now if you look at the area of this rectangle here, the area of that is 2 times 1, which is, 2 times, 1/2. The height of this is 1, that's 1, and this is 1/2. So that the base is 1 from 1 to 2, and the height is 1/2. So the area of the small rectangle is 1/2. So that means that 1/2, the area of that rectangle, is less than ln of 2, the area of this space, which covers more space than that rectangle. Okay? And now, let's look at a larger rectangle. Let's look at this rectangle here, where we take the height of the rectangle to be the height of this point at t equals 1. Now, if you look at this entire rectangle here, the height of that rectangle is the height of the point at t equals 1, which is 1 over 1. So the height of the rectangle is 1, and the base is also 1. So the area of this is 1. Right? So we know that ln of 2 is less than 1. element 2 is the area of this space, and it's less than the entire, so we're just going to be a square. There, it's less than 1. Okay? But we want to show it's less than 3/4. Okay? And so it could still be true it's less than 3/4. It could be, we need to find a sharper estimate. We need to find a better estimate for what element 2 is. It's less than, hopefully we can find it's less than a smaller number, 3/4. Okay, so if you look at the curve y equals 1 over t, it looks like this. Okay? And if you look at this curve, and then let's say you look at 2 points in that curve. Okay, look at 2 points on that curve, and then draw a line connecting those 2 points on the curve, a line segment. And notice what happens. The line segment is always above the curve itself. Okay, so if I take a line segment and connect 2 points on the curve y equals 1 over t, this line segment connecting these 2 points always lies above the curve. So let's do that with this curve. Let's connect this point and this point with a line segment. What will happen is that that line segment is always above the curve. Okay. So now instead of finding the area of the square, let's forget about all this extra space. This is all extra space. Now let's find the area of this triangle, where this is the hypotenuse. So now we're looking at this triangle. And if you see the area of the triangle, this takes up more space than the area below. So if you take the area of this rectangle plus the area of that triangle, it takes up more space than the area under the curve, or element of 2. It would be more than element of 2, right? So what is the area of that triangle? The base is 1. And the height of this is 1, and the height of that is 1/2. The height of this is 1/2, and the height of the whole thing is 1. So what's left is 1/2. Does that make sense? So this point has a height of 1. This point is in line with this one. This is 1/2 up, and that's 1 up. So the rest of it is 1/2. That's 1/2. And so the area of that triangle is 1/2 base, which is 1, times height, which is 1/2. So the area of that triangle is 1/4. So that triangle has area 1/4. Okay? So that means that the area under this curve, or element of 2, is less than the area of the rectangle plus the area of the triangle. Okay? So let me write it here. Element of 2 is greater, we already showed it's greater than the area of that rectangle, which is 1/2. It's also less than the area of the rectangle, which is 1/2, plus the area of the triangle, which is 1/4. So element 2 is strictly greater than 1/2 and strictly less than 1/2 plus 1/4. Therefore, 1/2 is less than element 2, less than 3/4. 1/2 plus 1/4 is 3/4. And so we get the inequality here that we want to show. We want to show this, and we got that right here. We're done. With part A. Okay. Okay, so now let's go to part B. So maybe okay, so it's the same example, but part B. Use the midpoint rule. With n equals 10 to estimate the value of element 2. Okay? So use the midpoint rule with n equals 10 to estimate the value of element 2. Let's draw the picture again. This is the t-axis, this is the y-axis. This is y equals 1 over t. This is y equals 1 over t. This is t equals 1. And let's stretch this out. I'm not drawing this to proportion. So this is less than that. So we're going to look at from t equals 1 to t equals 2. And so n equals 10. And so what that means is we want to separate this into 10 equal subintervals. So that's, okay, so it's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So now I've separated the interval from 1 to 2 into 10 subintervals, equal length. So we're going to use the midpoint rule. So the midpoint rule, if these are in tenths, this would be 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, 1.9, and 2, right? So it'd be 1, 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, 1.9, and 2. Okay, we're going to use the midpoint rule. And so the midpoint rule says take the midpoint of each subinterval. So the midpoint of the first subinterval, the midpoint of the second, the third, the fourth, the fifth, the sixth, the seventh, the eighth, the ninth, the 10th. So we take the midpoint of each of those 10 subintervals. Now the first subinterval goes from 1 to 1.1, so the midpoint is 1.05. The next midpoint is 1.15. The next midpoint is 1.25. The next midpoint is 1.35. The next midpoint is 1.45. The next midpoint is 1.55. Next midpoint is 1.65. The next midpoint is 1.75. The next midpoint is 1.85. And the last midpoint is 1.95. So I just drew there were the values of the 5 midpoints. You have 1.05, 1.15, 1.25, 1.35, 1.45, 1.55, 1.65, 1.75, 1.85, 1.95. Those are the 10 midpoints of the 10 equal length subintervals from 1 to 2. Okay, and so to estimate the value of element 2, we just make 10 approximating rectangles, where the height of each rectangle is determined by the height of the function at the midpoint of each subinterval. So these are the values of the function at those 10 midpoints. And so at each midpoint, we're going to correspondingly make the rectangle have a height, the height of the function at that point in that subinterval. And so what you get is you get 10 approximating rectangles. Okay, and so now we get those 10 rectangles now from the heights of the function at those 10 midpoints, those 10 subintervals, and now I drew those 10 rectangles. Those are 10 approximating rectangles, so the area under the curve y equals 1 over t from t equals 1 to t equals 2. So now we're just going to add up the areas of those 10 rectangles by just taking the height of the function at each midpoint, multiplying it by the length of each subinterval, which is 0.1. Okay? So by the midpoint rule, we get that ln of 2, which is the interval from 1 to 2, 1 over t dt, is approximately the sum of the areas of those 10 approximating rectangles, which is f of so here f of t is 1 over t. Okay, so I'm calling f of t 1 over t. So it's going to be f of 1.05 times 0.1 plus f of 1.05 times 0.1 plus f of 1.15 times 0.1 plus f of 1.25 times 0.1 plus f of 1.35. That's 1.25 times 1 plus f of 1.35 times 0.1 plus f of 1.45 times 0.1 plus f of 1.55 times 0.1 plus f of 1.65 times 0.1 plus f of 1.75 times 0.1 plus f of 1.5 times 0.1 plus f of 1.95 times 0.1. Okay, good. Okay, so this is the areas of those 10 rectangles. This is the area of the first rectangle, base times height, plus the area of the second one, plus the area of the third one, plus the area of the fourth one, plus the area of the fifth one, plus the area of the sixth one, plus the area of the seventh, plus the area of the eighth, plus the area of the ninth, plus the area of the 10th. Okay, so those 10 squiggly underlines are squiggly underlining 10 products. Each product is the area of another one of those approximating rectangles in order from the first one to the 10th one in that picture. Okay, so if you add up those products, you get the number 0.693. Okay, so ln of 2, which is that differential, is approximately 0.693. So that's an estimation for ln of 2, 0.693. That's part B. Okay, so we're done. So, estimate the value of ln of 2. We did that. That was cool. We did that right here. Okay. Yeah, let's keep going. Okay, so using the fundamental theorem of calculus, we have, okay, so using the fundamental theorem of calculus, we have, so using the fundamental theorem of calculus, we have that the derivative dx of the integral from 1 to x of 1 over t dt is equal to 1 over x. Okay? Or the derivative ddx of ln of x is 1 over x. And so this is what we will be using. The ddx of ln of x is 1 over x. Okay. All right, so we have that equation, dx of x and 1 over x. And next is laws of logarithms. Okay, so laws of logarithms. If x and y, so if x, y are positive numbers and r is rational, meaning a fraction, so x and y are positive reals and r is a rational or a fraction, then 1 ln of x times y is equal to ln x plus ln y. 2 ln of x over y is ln x minus ln y. And 3 ln of x to the r is equal to r times ln x. Okay, so those are 3 laws of logarithms. So we have this equation here, and we have 3 laws of logarithms. So I'll stop and give you a chance to write it down. Okay, so those are the 3 laws of logarithms. Okay, so next I'm going to prove some of this. Okay, so let's first prove the first law of logarithms. Proofs. So proofs. And so let's prove number 1. Let f of x equal to ln of ax, where a is a positive constant. Okay. So f prime of x is equal to 1 over ax times a, which is 1 over x. Okay. Ln of x, ln x, the derivative, that means the derivative of that function, the derivative of ln of x is 1 over x, from what I wrote previously, right? So that means that this function, ln of ax, actually, okay, so I want to emphasize this. That function, that function is f. The derivative of that function is 1 over x, and the derivative of this function is 1 over x. That implies that ln of ax and ln x differ by constant. Okay, so when two functions have the same derivative everywhere, that means they differ by a constant. And so that implies ln of ax equals ln x plus c. Okay, let x equal 1. Then ln of a times 1, which is a, is equal to ln of 1 plus c. Well, ln of 1 is 0. Okay, so how do I know that? ln of 1 is the integral from 1 to 1 of 1 over t dt. And the integral from something, when the lower and upper limit are the same, we showed earlier by the properties, is 0. So ln of 1 is 0, so that's 0 plus c, which is c. So that means ln of a is c. And so that implies that ln of ax is equal to ln of x plus ln of c is ln of a, which is plus ln of a. So we just showed ln of ax equals ln of x plus ln of a. Okay? And so what you can see is that this is like having x and y. If you let y be a, so y is positive, so is a. ln of product of these two things is the sum of their ln's, right? So that's proof right here. So I prove that right here. Okay, so that's the proof of 1. Okay, so I'm going to erase this and prove 2. And what I'm going to do is I'm going to keep that check there because we've now proven 1. So we now have 1. Let's prove 2. Okay, proof of 2. So ln of 1 over y plus ln of y is equal to ln of 1 over y times y, right? Where x is 1 over y and y is equal to y. ln of 1 over y plus ln of y is ln of 1 over y times y. This is by property 1, that equals sign is from 1, which we already proved. And so that's equal to ln of 1. 1 over y times y is 1. And ln of 1 we already showed is 0. That implies that ln of 1 over y is equal to negative ln of y. Okay? So, ln of x over y is equal to ln of x times 1 over y. And by 1, ln of x times 1 over y would be ln of x plus ln of 1 over y. That would be by property 1. But now, ln of 1 over y is equal to negative ln y. So this is equal to ln of x. So instead of ln of 1 over y, I'm going to say it's equal to minus ln of y. That's what I just showed us, that ln of x over y is equal to ln of x minus ln of y. And it's proved there. That's now proved 2. Okay, what I showed is ln of x over y is equal to ln of x minus ln of y. So that proves the second law of logarithms. Okay. Okay, so that's the proof of the second law of logarithms. ln of x to the r. So while ln of x to the r is equal to ln of x times x times x times dot 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 times x, and there's r of them. Right? X to the r is the product of r, x with itself, r times. That's x to the r. Okay. Well, ln of x multiplied by itself r times is just ln of x times x times x times times x, where there's r minus one of them. Right? And ln of x times that is just equal to ln of x plus ln of x times times x, where there's r minus one of them. So what I did was, I started with ln of a product of r x's, and I said it's ln of x plus ln of a product of r minus 1 x's. And so you just repeat this process, r times in total, meaning this was the first time, and do it r minus 1 more times, and you get that this is equal to ln of x plus ln of x plus plus ln of x, and where there's r, ln of x's, r of them. And if you add up ln of x r times, that's equal to r times ln of x. So I just showed us r ln of x is equal to ln of x to the r. ln of x to the r is equal to r times ln of x. That's right. That's the third law of logarithm, and that's proved also. That's proved right here. Okay, so now those are the 3 laws of logarithms, and we proved all 3. Okay, good. Okay, so let's keep going. Let me just check the camera real quick. Okay, the camera is good. Let's keep going. I raised the camera this lesson so I think you can see the board a little bit better. Okay, so next example, is expand the expression ln of x squared plus 5 to the 4th power sine x over x cubed plus 1. Okay, so expand that expression. Proof. Ln of x squared plus 5 to the 4th sine x divided by x cubed plus 1. Okay, so let's expand it. So by the second law of logarithms, we can say that ln of the numerator, the ln of this fraction is ln of the numerator minus ln of the denominator. Okay, so that's the second law of logarithms. The second law of logarithms says ln of x over y equals ln of x minus ln of y. But instead of x and y being, instead of using x and y in the numerator and denominator respectively, x and y just represent 2 unknown values, right? And so instead of that unknown value being x or being y or being just a single variable, that unknown can be an expression of x. So here, instead of the numerator being x, it's now an expression of x squared plus 5 to the 4th sine x. And instead of the denominator being y, now it's another expression of x cubed plus 1. Okay, so ln of an expression of x divided by another expression of x is equal to ln of the numerator expression of x minus ln of the denominator expression of x. Okay, so that's by the second law of logarithms. Now next, I'm going to put the equal sign here. I know it doesn't line up, but it'll give you more space. So ln of this is, you can think of this as the ln of the product of 2 functions, x squared plus 5 to the 4th and sine x. And so by the first law of logarithms, you can say that ln of the product of those 2 functions is ln of the sum of the ln's of those functions. So ln of x squared plus 5 to the 4th plus ln of sine x. That is now what this first ln is. That is equal to this by property 1. Okay, and then this is minus ln of x cubed plus 1. Okay, now this is x cubed plus 1. Okay, keep that in mind. So we can't expand that any further. Now, by the third law of logarithms, I can move this 4 in front and say this is equal to 4 ln of x squared plus 5 But this is still plus ln of sine x and minus ln of x cubed plus 1. Okay, so what I did was I took ln of x squared plus 5 to the 4th and made it 4 times ln of x squared plus 5 by property 3 on the law of logarithms. Okay, and so now I've expanded that expression as much as I can. That is as much as I can expand it as possible. Ln of that fraction is equal to 4 times ln of x squared plus 5 plus ln of sine x minus ln of x cubed plus 1. Okay, and that's expanded as much as possible. I cannot move the 3 in front here because it's x cubed plus 1. I would have to cube everything in the ln in order to move it to the front. The 3 is only cubing the x, not the plus 1. So I can't move it. Here I can because I'm raising to the 4th everything else in the ln. That's why the 4 can move to the front. The 4 is raising this whole thing to the 4th. This cube is not raising the whole thing to the 3rd power. It's only raising x. And so that's why I can't use the 3rd property to move the 3 in front there. I have to keep that x cubed plus 1. Okay? And so this is expanding the expression. Okay? So sometimes I will call proof answering a question because you can think of all the math you're doing as proofs. Okay? Okay, so next example. Okay, so next example is express ln A plus ln A minus 1/2 ln B as a single logarithm. Okay, solution. Okay, so ln A plus ln A minus 1/2 ln B is equal to 2 ln A minus 1/2 ln B. So I just combined the ln of A and ln of A to get 2 ln of A. Right? Okay. So that's equal to 2 ln A minus 1/2 ln B. Okay, now that's just algebra. Now here, what I'm going to do is I'm going to express 2 ln of A as ln of A squared by the 3rd law of logarithms. I'm going to go in the opposite direction. Okay? It says ln of x to the r equals r ln x. I'm starting with the r ln x here, and I'm rewriting this ln of x to the r. It's an a. Okay, so 2 ln of a is equal to ln of a squared. That's by property 3. And it's minus 1/2. Actually, I'm going to do the same thing also here. I'm going to take ln of b, and that's minus ln of b raised to 1/2. And so now that expression, I'm expressing like that, also by the 3rd law of logarithm. Okay, I'm moving the coefficient to the exponent, which I'm allowed to do by property 3. Now ln of a squared minus ln of b to the 1/2 is equal to ln of a squared over b to the 1/2. So difference of 2 logs is just a single log and the fraction where that's the numerator and that's the denominator. Okay, and so now that is expressing ln of a plus ln of a minus 1/2 ln of b as a single logarithm. That's a single logarithm. Ln of a squared over b to the 1/2. Okay, and that. So that's the solution to that example. Okay. Good. So if you look at this graph, this is the graph of y equals ln x. Okay, so y equals ln x is a continuous. You can draw the graph without using your hand, so it's continuous. It's a continuous, increasing. So it's increasing function because as you move from left to right, the values increase. So as you move to the right, the values the values increase. So it's an increasing function. So y equals ln x is a continuous, increasing, concave down function. Okay, so a concave down function, this is a concave down function. Right? That's a concave down function, that's a concave up function. Okay, so this is a concave down function, and in fact it's the left hand side. It looks like that part of it. It looks like the part that's increasing but concave down part. The left side is increasing concave down, the right side is decreasing concave down. This is decreasing concave up, that's increasing concave up. Okay. So our graph is concave down, and it looks like that part. Okay, so y equals ln x is a continuous increasing concave down function. Also, limit x approaches infinity of ln x equals plus infinity, and limit as x approaches 0 to the right. Okay, so limit as x approaches infinity of ln x is equal to plus infinity. Limit as x approaches 0 to the right of ln x is negative infinity. Okay, so as x increases arbitrarily, gets larger, arbitrarily large, the value of ln x increases, gets arbitrarily large also. And also, as x gets closer and closer to 0 to the right of 0, the value of ln of x tends to negative infinity. So as x gets closer and closer to x equals 0 from the positive direction, the value of ln x tends to negative infinity. Okay, so that's a loose interpretation of what a limit with these limits mean. Okay. Definition. Okay, so e is the number such that ln of e is equal to 1. Okay, so e is the number, in fact it's the only number, unique number, such that ln of it is 1. So ln of e is 1. Okay, so if you put, let's say, e somewhere over here, the value of e, ln of x at e, is 1. So ln of e is equal to 1. And the number e is approximately 2.71828. And it continues. Okay. E is irrational. So e is irrational and thus not repeating. E is irrational and thus non-repeating. Okay. E is irrational means that you cannot express e as a fraction, which is a quotient of one integer over another non-zero integer. Okay, that's the definition of e. E is a number such that ln of e is 1. Example, differentiate y equals ln of x cubed plus 1. Okay, so example, differentiate y equals ln of x cubed plus 1. Okay, so note, remember I'll propose a note here. Remember we have d dx of ln x is 1 over x from earlier forward. We use the fundamental theorem of calculus to show that d dx of ln x is 1 over x. Okay, so we're going to use that. Differentiating dy dx is equal to the derivative of that. Dy dx is the derivative of ln of x cubed plus 1. Well, what's the derivative of ln of x cubed plus 1? The derivative of ln of x is 1 over x. And so what that means is, I'm going to erase this now. What that means is that the derivative of ln of a function of x, so ddx of ln of f of x is equal to 1 over f of x, because that's what's in the ln, but then times the derivative of that function, which is times f prime of x. That's using the chain rule. So ddx of ln of a function of x is equal to 1 over f of x times f prime of x. Or you could say, though I like this way because it's kind of illustrating, showing you the process of how you get that. But you can write this a little bit more succinctly by saying ddx of ln of f of x is equal to f prime of x over f of x. Okay, so I give you these two formulas. ddx of ln x is 1 over x by the fundamental theorem of calculus. By this equation here, I show that ddx of ln of f of x is f prime of x over f of x. Okay, so here, the f of x is x cubed plus 1. So ddx of ln of f of x is equal to f prime of x, which is the derivative of that. So it's equal to the derivative of x cubed plus 1 divided by x cubed plus 1. Okay, so the derivative of y equals ln of x cubed plus 1 is equal to the derivative of x cubed plus 1 divided by x cubed plus 1. And the derivative of x cubed plus 1 is 2x divided by x cubed plus 1. And that's it. That's done. Okay, so use this formula and use that formula. And now the check means that I want you to use those formulas. Okay? So these two formulas are important to know. Okay, and we use this formula here to get that answer. That's this formula using the chain rule, combined with the chain rule. Okay? Okay, so that's that example. All right, so reminding you what the chain rule says. The chain rule says that if you have, the chain rule says, along with conditions, that the derivative ddx of f of g of x is equal to f prime of g of x times g prime of x. Okay, that's what the chain rule says, and so that's how I got this. Because this is coming from the fact that, so if you use that chain rule, what that's saying is then that when we take the derivative of ln of f of x, here f and g are just arbitrary general functions, so here ln is really f and here f is really this g. So if you take f prime of g of x, f prime of g of x would be the derivative of this function. The derivative of ln of x is 1 over x. So it's the derivative of ln of something, which is 1 over that something, which is f of x. So f prime of g of x is that fraction, times the derivative of what's in here, times f prime of x. And so we're getting this from the chain rule. Okay? Okay, let's keep going. Trying to erase the order in which I wrote things down. Okay, so that's the last thing I wrote down. I'm going to erase that now. Okay. Okay. So next example. Find ddx of ln of cosine x. Solution. Find ddx of ln of cosine x. Okay, so ddx of ln of cosine x is, well, so by my formula, right, let's call that f of x. Let's call cosine x f of x. By my formula, d dx of ln of cosine x is just f prime of x over f of x, where f of x is cosine x. That means that's equal to the derivative d dx of cosine x divided by cosine x. Cosine x is f of x. And derivative of cosine x is negative sine x. And that's over cosine x. So you get sine x, negative sine x over cosine x, that's negative tan x. And so the answer is negative tan x, right? Tan x is sine x over cosine x. And so negative sine x over cosine x is negative tan x. And so that's the answer. Okay, next example. Differentiate f of x equals to the square root of ln of x. Okay, so these are asking the same question in a different way. Saying find d dx of a function is the same as differentiating, saying differentiate a function. Okay, so let's do that. We're going to differentiate f of x. Solution. Okay, so differentiating means finding the derivative. So what is f prime of x? It's equal to the derivative of ln of x raised to the 1/2 power. So I'm just adding into this step. I'm making this step, instead of f prime of x, I'm writing d dx of it. And then I'm writing this in exponential form. Instead of writing the square root, I'm taking that and raising it to the 1/2 power. Okay? So another formula. So another formula is that d dx of a function raised to the nth power is equal to n times that function raised to the n minus first power. Okay? And again, this uses the chain rule. So I'm going to put a check next to this. Check means now remember this formula. So d dx of f of x to the nth power is equal to n times f of x to the n minus first power. So let's apply that formula here. Wait, one more thing. Dx of f of x to the n is n times f of x to the n minus first power times f prime of x. Okay, that's the formula. Okay, so that's a formula, so use that. So let's apply that to this problem. So d dx of ln x to the 1/2 power is equal to 1/2 times ln of x. And then you take the original exponent and subtract it by 1. So 1/2 minus 1 is negative 1/2 times the derivative of ln x. And derivative of ln of x is 1 over x. So this is 1/2 times ln x to negative 1/2 power times 1 over x. Okay, derivative of ln of x is 1 over x. And so then that's equal to 1 over 2 times x times the square. Negative 1/2 means you move the 1/2 power to the denominator. So ln of x to 1/2 in the denominator is the square root of ln of x. So you get that the f prime of x is 1 over 2x times the square root of ln of x. Okay. And so that is the end of that proof. At the end of this proof was right here. Okay, so we now answered those two problems. And so for this problem, I use this formula. Okay, so I'll give you a second to look at this, and then I'm going to erase these two, and I'm going to keep that, and I'm going to prove this formula. Okay, so first we use the formula. Here. But then to really complete this example, we have to prove the formula that we used in the example, right? So after I prove this formula on the next board, then we'll really be complete with this example. Then we will have really justified this equals sign, because we use that formula to say this equals sign here. And then everything is good. Okay. Okay, in a mathematical proof, that would be called like a claim. Okay, so I'm going to rewrite it. I'm just going to rewrite the exact same thing here. Claim. My claim here is that, so in a mathematical proof, you would maybe make that as part of your proof, and then afterwards you would say claim, or maybe before you'd say claim that equal sign, and then later you would use it, and it would be justified with the proof of the claim. So here the claim is that the derivative of f of x to the nth power is equal to n times f of x to the n minus first power times f prime of x. Okay, that's the claim. So now let's prove the claim. So proof of claim. So this would be like a part of the mathematical proof, proving that claim. Okay, and so to do that, we're going to use, to do this proof, we will use the chain rule. Okay. So again, reminder, chain rule tells you that the derivative of f of g of x, let me put a bracket here, the derivative of f of g of x is f prime of g of x times g prime of x. And so we're assuming that we know the chain rule is true, right, from earlier. Okay? So applying that here, okay, let g of x equal x to the n. Actually, let g of y equal y to the n. Okay? So the only thing is here, f and g are just arbitrary functions. And so the f and g in my proof is going to be the opposite. So the f in the claim is going to be applied to the g in this formula. And the g there applies to the f in the formula. Okay? F and g are just arbitrary functions. And so the function that goes here does not need the name g, and the function there does not need the name f. Right? So if I made this, if I use this, but then this was h and this was, let's say, k, functions h and k, this should still hold, right? There's nothing significant about the names of the function, right? The names of the function are meaningless, right? The letters f and g are just the names of the function, and so they don't matter. And so I could instead call this function f and that function g, okay? And so in using the chain rule here, the function I'm going to put here, ironically, is called f, and the one I'm using here is the g, okay? That's because in my original statement, I'm using the statement with f, and I want to keep doing that because the point is to prove this statement. And so I want to use f to make the statement that I want to prove, okay? So this is not an inconvenient, this is the better way to do it because, again, f is the best letter to use for a function, and f is the easiest way to communicate a function to someone. And so I want to use f in the statement, okay? But the f in the statement should really go here where g is. Okay, let g of y equals y to the n. F of x to the nth power is the same as saying g of f of x. Okay, why is that? Because g is a function that takes the input and raises it to the nth power. And so g takes the input f and raises it to the nth power. So that's why f of x to the nth power is g of f of x. Okay, g again takes the input y and raises it to the nth power. So here g takes the input f and raises it to the nth power. So f of x to the n is equal to g of f of x. Okay? By the chain rule, g, the derivative of g of f of x, well, this way, by the chain rule, ddx of f of x to the n is equal to ddx of g of f of x. Because f of x to the n is g of f of x. Now dx of g of f of x by the chain rule, I'm applying the chain rule to this equal sign. Okay? So I'm going to put a star here. Because the star is the chain rule. So I'm applying the chain rule for that equal sign. And so this is saying this is equal to g prime of f of x times f prime of x. Well, what's, okay, so now g prime of f of x, g prime is n times y to the n minus 1. Okay, so let this be that, that's this. G prime of y is equal to n times y to the n minus first power by the power rule. So g prime of f of x, here the input is f of x. So that means that g prime of f of x is n times f of x, the n minus first power, right? Instead of the input being y, it's now f of x. And so y is a variable. So g prime of f of x is n times f of x, the n minus first power. And so g prime of f of x is n times f of x, the n minus first power. So this g prime of f of x here becomes n times f of x, the n minus first power. And then that's times f prime of x. Okay? And so what did I just show? I showed that d dx of x, f of x, the nth power is equal to n times f of x, the n minus first power times f prime of x. So I just proved that. And the claim is proved. The proof is that. Okay? Okay, good. Okay, let's keep going. Wait, I'll leave it on the board for just a second because it's good. Okay, so I proved that formula. So you can use that formula. Find d dx of ln of x minus 3 over the square root of x plus 1. Okay? So now we're going to find d dx of ln of that fraction. So solution. D dx of ln of x minus 3 over the square root of x plus 1 is equal to, so here what I'm going to do is I'm going to apply the laws of logarithms here to simplify the ln of that fraction. And then I'm going to take the derivative of the thing afterwards. This is going to be equal to d dx of, and in the bracket here I'm going to expand that ln. So this is ln of x minus 3 minus ln of the square root of x plus 1. So ln of that fraction is ln of the numerator minus ln of the denominator. And now that's equal to, this is by the second law of logarithms. The second law of logarithms says that ln of this is equal to ln of the numerator minus ln of the denominator. Okay? So ln of 2 substitutes the left thing I squiggly underlined with the right thing I squiggly underlined because they're equal by law 2 of logarithms. Okay. This is equal to d dx of this. I'm going to rewrite ln of x minus 3. There's nothing to do there. But then minus, this is minus ln of x plus 1 to the 1/2. Okay, so the square root of x plus 1 is x plus 1 to the 1/2. And so now that's just rewriting this in exponential form. And so this is equal to d dx of ln of x minus 3 minus, and now by the third law of logarithms, I'm going to take ln of x plus 1 to the 1/2, and I'm going to move the exponent in front as coefficient. This is minus 1/2 ln of x plus 1. Okay, and so I'm writing this expression as that one by the third law of logarithms. Okay, so now the derivative of that, this whole thing is the derivative of that minus that. And now this is equal to the derivative of the first thing minus the derivative of the second thing. Let me actually write them separately so we can just isolate each step and make a sense of it. This is the derivative of the first thing minus the derivative of the second thing, 1/2 ln of x plus 1. Okay, it's ln is equals the root of the first thing minus the derivative of the second thing. And so then that's equal to, what's the derivative ln of a function, right? Remember, note the derivative of ln of f of x is equal to f prime of x over f of x. Okay? So note the derivative ln of f of x is f prime of x over f of x. So here f of x is x minus 3. So derivative ln of x minus 3 is the derivative of x minus 3 divided by x minus 3. And this is minus 1/2 times the derivative of ln of x plus 1, which is the derivative of x plus 1 divided by x plus 1. Okay? And what is the derivative of x minus 3? It's 1. So this is 1 over x minus 3 minus 1/2 times the derivative of x plus 1, which is 1 over x plus 1. And that's it. So the derivative of ln of x minus 3 over the square root of x plus 1 is 1 over x minus 3 minus 1/2 times 1 over x plus 1. Okay? Okay, so let's leave it like that. Okay. Keep going. Okay, so actually I'm going to stop the lesson right here. This is a good place to stop, and so we'll continue with the rest of this section next time. Okay, so see you next time. Bye.